Hello, everybody, and welcome to the last part of chapter number 12 in Dynamics. This is Professor Algara with this small lecture. Well, hope it's going to be smaller than the first one. But anyways, we'll be covering a lot of things from 12.7 to 12.10 in the book, completing the whole chapter. We're going to talk about tangential and normal components when it comes into curvilinear motion. We will also be covering relative positions and things like that, and dependent movement. I think that will be all for today. I will be solving a few exercises for each one of those parts of the chapter, so stay tuned for more. Normal and tangential components. What I'll do in this part is kind of like go through the presentation and read what the book says, and then after that, as I always say, I will translate all these words into something that we can all understand based on my own approach. All right. So when a particle moved along a curved path, it is sometimes convenient to describe its motion using coordinates other than Cartesian. When the path of motion is known, normal and tangential coordinates are often used. In the normal tangential coordinate system, the origin is located on the particle. Thus, the origin and coordinate system move with the particle along. So what they're telling you is that you have an origin right here, but when you get into the particle itself, you will have to place a normal and tangential axis, a new one that it will be called O prime, and that one will be moving with the particle. So at t equals 0, that's where you have it, and then a few seconds or time after that, you will see it right here. That system will move with it. The t-axis is tangent to the path, at the instant consider. So if it's right here, this is the tangent, and then if it's right here, then it'll be another point. The normal axis is perpendicular to the t-axis with the positive direction towards the center of the curvature of the curve. All right, so the normal is always pointing to the center, normal to the tangent, and that's what we need to define. So the positive n and t directions are defined by the unit vectors. As you know from statics, right? Every time we're treating vectors, we always have a unit vector that is defining the direction of the vector in question. So the center of the curvature O prime always lies on the concave side of the curve. The radius of curvature, it's defined as rho. Um, so as you have, for example, right here, right? You have your particle, and then that particle has a normal and a tangent axis. Then you have an O prime, which is the center of the curve. That center of the curve always lies in the concave side of the curve. So when it moves to this one, for example, it'll be somewhere around here, as you can see on the picture. The radius, or that radius of the curvature, is always defined as rho, and that's the distance from the center all the way to the curvature or to the point in question. As you can see here, when you have a point, that point can be also placed in terms of differentials, and we always do that in a way to be able to deduct the equations, because when you take small differentials, all of them combined, it's what will tell you the real change. And that's just for position, all the things that you need to know in terms of that. When it comes to velocity, it's what we've covered in the first part of the chapter. You know that the velocity, it's always equals to the change in the position respect to the time, as you can see right here, or s dot as they call it on the book. For velocity, it's a little simpler because the vector velocity is always tangent to the path. Okay, and the velocity vector is tangent to the path, as I said, and it's positive with the path of motion. The magnitude is determined by taking the time derivative of the path function, when that is given in terms of t. V defined, the magnitude of the velocity, as you know, which is always the speed, and ut is the unit vector that defines that direction of the velocity. As we said, it's always tangent to the path, and that's why you see that ut. Okay. When it comes to acceleration, things get a little bit more complicated, and that's when you need to pay attention to this. So acceleration, as you know, is the time rate of change of the velocity, or as the equations are given right here, you know that is dv equals dt. But as we defined before, velocity is the speed that multiplies the unit vector, where we're talking about vectors right here. When you derive that, the magnitude and the direction respect to t, you will have to do these by parts, right? So that will be the time derivative of the speed times the unit vector, and then the speed times the time derivative of the unit vector. After a whole mathematical equation, we get to this, that acceleration is equals to this plus this, which is no more than the tangential component and the normal component. What it's important for us to know here, okay, and I will get into the mathematical manipulation because I will deduct this equation. But what is important for us to know here is that when it comes to acceleration at any point in curvilinear motion, we will always have a tangential component and a normal component. And both of them combined is what define the acceleration as a whole. Okay, it's a vector that has magnitude and direction. The magnitude is always giving us this, at and an, and the direction is given by the units vector. This is from statics, okay? When treating vectors, don't forget you have to have the unit, your magnitude and your direction. So when you have the two components, you will have a formula for each one of them. The tangential component is obtained by deriving, the velocity just as it is. If you have an equation of the velocity given and you derive that, that's how you get it. And then the normal component is given by the formula that we had over here, which is v, or the speed square divided by rho, which is the distance from this point to the curvature. All right. Then when you have that vector, in terms of AT and AV, and you want to get the magnitude, that magnitude will be obtained by taking, the square root of the normal component to the square plus the tangential component to the square. And that's it. So now that I've just went through the presentation pretty quickly, I just want to give you my insight, of this whole thing as I develop the equations myself. All right, I might be wrong, I might be right. I think I'm right, but whatever. Okay, something important for us to remember when we're talking about just rectangular components, right? You know that this is y and this is x. Everybody knows that. So that's your x axis and your y axis. When you have a point that we call P, if you want to locate that point in terms of Cartesian coordinates, that will be given by x and y component, right? And that's Cartesian. But now, if you want to know, you have to know that you can place the same point in terms of polar coordinates, which is given by the distance from the origin to the point, and that we always call r, or the radius, or whatever, and we also call the angle. So the same point can be defined as r, comma, the angle. And this is very important because I want you to remember that when working on curvilinear motion, and this is just from physics and math. You can actually locate a point using these two different coordinate systems. So now, all right, if I have then the curvilinear motion and I have a first point here, P, I'm gonna call P, and the same particle now move along this path to another point that is called P prime. I need to know the distance from an origin, right? And we covered that from here and also from here. As I said before, the distance from that origin to P is called r when we're working in polar coordinates, but I'm going to call this rho, right? And it's the same rho right here. If I see how much it moved from here to here, that little path that I'm just, marking will be called the position, or how it displays from one point to another. And I'm going to call this in terms of differentials ds. If I want to know the length of that arc, you know that the length of the arc is the radius times the angle in between. I'm just going to go and place that equation. So if I want to know the length of that will be equals to rho, which is, how much I have from here to here times theta. Or if I want to leave everything in differentials, I'm going to call that d theta. All right, so far so good. That equation is very needed for position, right? We're just talking position for now. We have from one point to another in order to get that. So if I now want to know the velocity, you know that velocity is equals to the the time change of the position respect to the time. If I do this, what is very important for us to know, more than this, is that when talking about vectors, velocity, it's also given by speed, and then that has to be multiplied by the unit vector that defines the velocity. And the velocity is tangent to the path. I'm going to take that unit vector, the tangential component, and then place it at this point. So for example, at P, I have velocity and the unit vector that defines the velocity, and I'm going to call that ut. At P prime, you also have a B prime, or that change per se, and then you have a unit vector that is called ut prime. Okay, so what I'm trying to tell you is that each one of those points will have its own velocity. All right. When it comes to acceleration, like I told you before, acceleration is why harder, because now we need to derive by part. Now we need to take into consideration the direction and the magnitude. So now for acceleration, we know that acceleration is equals to the differential, or the time change of velocity with respect to the time, which in this case, it's this guy right here. It will be the derivative of speed ut respect to the time. I will have to do this by parts, right? So if you remember differentiation by parts, I'm not gonna get into that, but it's u dot, or the derivative of the speed that multiplies to the unit vector tangential, and then plus the speed that multiplies to the time derivative of that unit vector in the tangential component. What we need to know is that these represents the magnitude, okay, and this is the change in magnitude, and this is the change in direction. And you can see these pretty easily, as you can see that ut just changed from this point to this point. So that change is what that time derivative will give me, this here, ut. And that's what we're going to concentrate now, because we need to calculate and work with that ut. And in order for us to do this, I'm just going to draw this again. Okay, so I had P and P prime, and I had the unit vector. I'm just going to go ahead and draw the unit vector, and I'm going to call that ut prime. So now what I need to know is to superpose those two vectors, one on top of the other, so you can see exactly what I mean by that. So we have this, and this is ut prime, and this right here, it's ut, and then the change on these vectors, it's what I will call the change on ut. Okay, so I just superpose this right here. Okay, I just took like a zoom, and I'm sorry, I'm a terrible drawer, I know that, but I'm just trying to make sense of all this theory, right? So the change on that unit vector is given by that. And why is this important? It's very important because you need to know that that little DUT will have magnitude and direction, and we need to place that in terms that we will actually understand. What we have between UT and UT prime, it's how this change from an angle, right? Or the change that you had from one point to another in terms of the angle. And don't forget that these ut and ut prime are just small differentials of the curve. So we're just approximating this to something that is straight. All right, so the way for us to actually know this, like I told you, you remember that I told you at the beginning that in order to know the length, you will have to multiply the distance times the angle. So the distance for us would be how much is ut and ut prime. Both of them are unit vectors, which means that if you want to get the magnitude of the ut, you will have to multiply the length of any of them times the theta, okay? The angle. So the magnitude, as I said, is 1 because it's a unit vector. So the ut it's equals to 1 because it's a unit vector that multiplies the theta. And I just use this equation as a base math for this. And then if you want to know the direction, right? Magnitude and direction of that particular vector, you need to know that that vector is pointing towards the center of the curvature, right? And we're going to call that a normal direction. Therefore, dut as a whole will be equals to d theta that is being multiplied by the unit vector going into the normal direction. So what you need to do now is that dut needs to be plugged, let me just go back, into this equation because you are looking for the change in direction. So what we need to do is that now this dut will be divided by time because we're deriving this respect to the time. So we get d theta, how it changed with the time, and then this multiplies to the un. So far, so good. And I want to know if you have questions until now because this is why hard to understand, especially if you're reading from the book. So once you get into this relationship, I need to call what I taught you at the beginning. And let me see if I can go back to this, utilizing this equation. The length of the arc, it's given by rho, and multiply that rho by d theta. So what I want you to do is take this equation and solve for d theta, which would be equals to ds over rho. And I want you to take this and plug that d theta into this guy right here. And if we do that, this is what we're going to get. Like I said, let me just rewrite everything so people don't get confused. dut respect to the time is equals to d theta over dt that multiplies un. Then from before, we know that ds it's equals to rho d theta. So therefore, we have that d theta is equals to ds over rho. And now I'm going to plug this into my equation that I had. So I will get ds over rho, this whole thing over dt, and then this multiplied to the unit vector. And if I rewrite this a little more, I get ds over dt rho unit vector. What is this guy? What is the derivative of the position respect to the time? Does anybody remember? Because we covered this quite a while. So this is the speed over rho that multiplies the unit vector. And this is du t dt. So now we need to take this into this part of the equation because we were solving just this. All right? Is everybody following me? Well, if you don't, then don't forget that you can email me. I can go through this like one by one and make you understand this. I'm just trying to explain you how to get, the equations, even though I know that you will be using just this. So if now I take this, I just want to rewrite my acceleration. Acceleration it's equals to speed times ut plus the speed that multiplies the, okay, and I'm going to plug what I just calculated into this part. So acceleration is equals to, this whole thing is no more than what we call the tangential component of the acceleration, and this it's v, also v over rho that multiplies the normal component. So therefore acceleration will be equals to at ut plus v squared divided by rho, and then the normal unit vector, which defines the acceleration. What you need to know ultimately is that acceleration is subdivided into tangential component in a normal component. So acceleration will have two components. The tangential one will be given by deriving the velocity respect to the time, and for that you will be given with information, and that particular one is always tangent to the path, right? And then you have the normal acceleration, which is equals to v squared divided by rho, and this is always normal, pointing to the center of the curvature or the center of the concave curvature. So therefore, acceleration it's equals to at plus an. Simple as that when you want to get the magnitude, sorry. All right, and this is pretty much the explanation if I go back to this. All right, a lot of different mathematical calculations and things like that that will take you into this, and I wanted to develop that for you so you guys can have an idea exactly of what we're doing here. All right, so usually raw has to be given. Usually you should have enough information for you to solve the exercises from the book, and those are the equations that you will need to solve them. As always, I have an exercise for you so we can solve it together, and this whole thing could make a little bit more sense. All right, so let's just solve the exercise. So a car travels along the road with a speed of 2s meters per second, where s is in meters, and then they give us rho, which is equals to 50 meters, and they're asking us to find the magnitudes of the car's acceleration at s equals 10 meters per 10 meters. So we need to calculate, the plan will be to calculate the velocity when s is equals to 10 meters. But before I do any of this, based on what we have, you can know, that if you want to know the acceleration is equals to dv, the change of dt, right? And then velocity is also ds dt. If you know those two equations, that will give you an idea on how to start these exercises. So if velocity is given in terms of s and they're asking me the acceleration when s is equals to 10, the best course of action will be to calculate the velocity when s is equals to 10 meters, using the equation that was given. And then after that, we just need to calculate the tangential and normal components of the acceleration. It's very simple. We have to derive this equation, and then after that, we have to calculate the normal component as we did it before. So we need to be organized, and we're going to plug the data that we have. We know that the velocity it's 2s meters per second. And then you also know that rho is equals to 50 meters. And they're asking us the acceleration at s equals 10 meters. So it's It's very simple. We're going to calculate the velocity at 10, and that's V10. And it's no more than multiply this by 10, obviously, and this is 20 meters per second. So now I have to remember that I have to calculate normal acceleration and a tangential acceleration. So the normal acceleration already have formula, which is v squared divided by rho, and then the tangential is the derivative or the change in dv dt. And we can use that, or we can use another equation, as you remember, a ds equals v dt. And the reason why is because the velocity is given in terms of s, not in terms of t. So the first equation will not work. So we're going to use this. I'm going to go ahead and calculate the normal component first, which is 20 to the square divided by 50. And that will give me 8 meters per second square. Perfect. Now for the tangential, I'm going to use a ds. It's equals to v dv. It was dv, sorry, not dt. So I will solve this in terms of acceleration. So I will get that acceleration it's equals to dv over ds, and then this multiplies v. So now I can derive the velocity with respect to s and multiply that by the magnitude of the velocity, and that should give me the value that I'm looking for. So in this case, I will get that the tangential acceleration is equals to the derivative of v respect to s, and then this whole thing is multiplied by the speed calculated at 10. So I'm going to go ahead and leave that outside, which is 20. And then the derivative of 2s respect to s will be equals to, that's 40 meters per second square. All I have to do is to use the equation that we developed, which is tangential component to the square plus normal component to the square root of all of that. That will give you, all right, and that will be the result of our exercise. All right, so now we're going to be talking about dependent motion, one of the easiest part of the chapter number 12. So usually when you have two different blocks, right, or more than two blocks and there is fully involved, the movement on one block will be affected by the movement of the other one. Or let's just read what it says. So in many kinematics problems, the motion of one object will depend on the motion of another object. The blocks in the figure are connected by an extensive cord wrapped along a pulley, as you can see here. If block A moves downward, then block B will move up the other incline. So the motion of each blocks can be related mathematically by defining position coordinates SA and SB. Each coordinate axis is defined from a fixed point or a datum line measured positive along each plane in the direction of motion of each block. So in this example, for example, as you can see, position coordinates SA and SB can define from a fixed point or datum lines. That datum lines are basically the ones that you can see here or right here. The little green ones that you can see here or here. Okay, so and from the center of the pulley along each one of block A and B. If the core has a fixed length, the position coordinates SA and SB are related mathematically by the equation, like LT, it's equals to SA plus the little distance between CD, which is the thing that is wrapped around the pulley, plus SB. Okay, and with that, LT is the total length of the cord, and LCD is the length of the cord passing over the arc CD over the pulley. All right, so far so good. So if you have that and you have that equation, the good thing with this is that you can get equations for acceleration, position, velocity, and all of those things. The velocity of the blocks L and B can be related by differentiated the equation that I had before, right? So LCD and LT remain constant. So if that's the case, right, and we want to use the derivative of LT will be equals to the derivative of SA respect to t plus the derivative of LCD, which is the thing passing over the pulley, dt, plus the derivative of SB over dt. What is important to know is that since this is constant, the derivative will be zero, and this one will be zero as well. And if those are zero, this equation can be rewrite as zero. It's equals to BA plus BB, or BA, it's BB is equals to minus or negative BA. The negative sign indicates that A moved down the incline and B moved up the incline. Okay, accelerations can be found by differentiating the velocity expression, and then that will prove to yourself that sorry, A AB is equals to negative AA. Very similar to the velocity and very easy to follow. Consider a more complicated example. Position coordinates SA and SB, as you can see here, are defined from fixed datum lines that are placed right here on the top and right here on the pulley. Okay. Measure along the direction of motion of each block. Note that SB is only defined to the center of the pulley above block B, since this block moved with the pulley. Also, H is a constant. The red color segments of the core remain constant in length during the motion of the blocks. So the position coordinates are related by the following equation. So as you can see, we have SB right here and SB right here. So that's 2 SB plus H plus, right, that's H, this whole thing, plus SA, which you have here. And you also have a constant of all these little pieces over the pulleys that are always remain constant, and this will be equals to the whole length. I can actually, since both of them are constant, I can send this over to here and subtract that in order to have a more simplified equation. It's equals to the total length, and as you can see here, you know, so since LT and H remain constant during the motion, the velocities and acceleration can be related by two successive time derivatives. So what we're doing is exactly what we did before. So if we want to get the velocity and acceleration for each one, all we have to do is utilizing the equations that we'll be learning. Velocity is ds over dt, and once you have that, you know that acceleration is equals to dv over dt. By getting that, then you can get an equation of velocity, position, and acceleration just by relating all of this length of the chord. So when block B moved downward, the block A moved to the left, and that's why you have the sign convention. But you have to be consistent with this. You have to know exactly when it's positive and when it's negative. This example can be also worked, by moving the datum to another place. So at first we had the datum right here on top, but now we're going to have the datum on the bottom. If you have the datum of the bottom, the distance from the datum to your point B will be called SB. And if that's the case, then the equation will be rewritten as this. So this whole thing is H and this is SB. So therefore, what you have here will be the remaining of the core, and that's what you're looking for. So 2 times H minus SB is what will give you that component, okay? So in the past, when you move the datum, SB was just placed right here. What I'm trying to show you with this is that you can get two different equations as you move the datum. and then velocities right here, accelerations right here, and then just prove to yourself that the results are the same. Okay, regardless, we just move the datum and we will get the exact same thing. What is important about this is that we can put all these procedure into one single slide so we can simplify things. So these procedures can be used to relate the dependent motion of particles moving along rectilinear path. Only the magnitudes of velocity and acceleration change, not their line of direction. So first we need to define position coordinates from fixed datum lines. That's the most important thing, okay? Then after that, you need to relate the position coordinates to the chord length. Segments of the chord do not change in length during the motion, and you can leave them out. You don't need to calculate them because they will not change. If a system contains more than one chord, you have to build an equation for each one of those chords. You have to have an equation for chord number one and then another one for chord number two. I'm pretty sure those two equations will be able to be related as they might be common in one point. And then you will differentiate the position coordinates to get the velocities, and if you want to get the accelerations, then you will have to differentiate one more time. Something very important, you need to keep track of your signs. Okay? And again, we're going to solve an exercise so we can know exactly what to do and how to do it. So in the figure on the left, as you can see here, you have a chord, and then A is pulled down with a speed of 3 meters per second. We need to find the speed of block B. So all we have to do is very simple. At first, following what we said before, it's to place the datum. So our datum will be at a fixed point right here. So the distance from the datum to A will be called SA, and the distance from the datum to the point D will call SD. Remember, this is treated as a point, even though you have a hook and everything, but we're not studying that because we're going with a more general case. So the data we have for this exercise, right, is that VA it's equals to 3 meters per second, and they're asking us for BD. Okay, so what is the total length of this? The total length of this will be equals to SA, which is this, plus 3 times, because you have 1, 2, and 3 SD. And then obviously, if you want, you can add the constant, but like I said, you can leave them out as they're not going to take into consideration. You can think of that as the total length, as a subtraction of the length minus those little pieces. So if you want to get velocity, that will be equal to the differentiation of ds dt. So the derivative of that would be equals to BA plus 3 BD. And the reason why it's positive is, remember, I'm trying to place my sign convention going down as positive, but if you place it differently, that doesn't matter at all, okay? So BD will be equals to VA minus VA divided by 3. And for us, that would be minus 3 over 3, which is equals to minus 1 meters per second, or if you had it differently, it's just 1 meter per second going up. Okay, and your sign convention is respected. At the end, we're all going to get the same result. So recapping a little bit, what is important is that we place the datum at a fixed location and that we can establish our sign conventions, and it'll be different from each one of us. Then after that, you place your length equation, you derive that in order to get velocity, and if acceleration is needed, then you might do the same thing. So relative position, one of the easiest topics in the whole book. So the absolute position of two particles A and B with respect to a fixed X, Y, and Z reference frames are given by RA and RB. The position relative of this can be given by relating these two equations. So this is what I want you to understand right here. And let's just pay attention to this picture. So you have a fixed observer. That's the important thing, right? And then you have a translating observer, which is another point. And then you have a third point. So we have 3 points involved right here. So from the fixed observer, you can see that, the distance, you can see your distance from this fixed observer all the way to the first traveler, which will be called RA. And then from the same point, you can also see the other particle, which will be called RB. So what we're trying to do here is to relate the traveling observer and B. So you can actually get a perspective of B going to from A, or the position of B related to A. If you want to relate those equations, it's very simple. But the importance here is that if I already establish RB and RA just by using vectors or mathematical equations with vector, you can get your vector RBA, which is just a result of using RA and RB. With that, the equations will be rewritten as RB, it's equals to RA plus RBA, right? If you have the three vectors, your RB will be the sum of this plus this one. And the whole thing with this is that when we have three components in movement, we can relate them all by putting them into one equation. For velocity will be exactly the same thing, as you know that position and velocity, they are related with the derivative. Velocity it's equals to ds respect to the time. So if I do that and I derive the equation that I just had, I will get that bb it's equals to ba plus b respect to the a. Okay. In these equations, BA and BB are called absolute velocities, and then BBA, it's a relative velocity of B respect to A, or of B by looking from A or something like that. When it goes to relative acceleration, it's exactly the same equation. So by deriving that, you know that acceleration is equals to the derivative of V respect to T. And if that's the case, then AB will be equals to AA plus the relative acceleration of B related to A. And those three equations are the only ones that I need in order to cover this topic pretty much, okay? Like I said, you have these three things involved, your fixed observer, your traveling observer, and then another particle. If you want to relate them all, you can use that by using vectors, okay? And those vectors are just, summing or subtracting the vectors in order to get that equation. In this case, I'm just summing the two vectors in order to get BB, okay? So how do we use this to solve problems? And that will depend, okay? Since relative motion equations are vector equations, problem involving them might be used in one of two ways. For instance, the velocity vectors in BB equals to BA plus BBA could be written as two-dimensional Cartesian vectors, and the resulting 2D scalar components equation solved for up to two unknowns. Alternatively, vector problems can be solved graphically by using trigonometry, and this approach usually makes sense for the law of sines or cosines. What I'm trying to tell you here is that you can, when treating with vectors, you can use the equations that you learn in physics and also in statics, for the magnitude and also the angle. But if you have them placed beautifully, then you can use, the law of sines or cosines in order to solve the exercises. And a little bit of reminder what the law of sines of cosines are. Right here, I'm just writing this for you, and I will post this on Blackboard so you can have it. And I want to give you an example of that. You have two aircraft that are shown as you can see here. So you have the first one and the second one, and what they're looking us to find is the velocity of B respect to A. All right, so I'm going to solve these exercises by vectors and also by just using trigonometry. Okay, so by vectors, what is important here is that we place BA and BB in a way that we can understand what's happening, and that's what I'm going to do. So I have BA right here, and I have BB, and I don't have to say that, but these are just vector, and I know that I have 60 right here, right? That's the information that is giving. What I need to do now is just write these velocities in terms of vectors. So for BA, I have 650 going into the I direction. That's all I have. For VB, I will have to decompose this velocity using cosines of 60 and sine of 60 in order to get the components. So the first one would be minus 800 that multiplies cosine of 60 and I, and then minus 800 that multiplies, I'm sorry, 800 that multiplies sine of 60 in the J direction. If I keep solving this a little bit more, I will get that BB is equals to minus 400 I minus 692.8 J, and don't forget your units, kilometers per hour. And this is kilometers per hour. All right, that's the vector method, the one I was solving. So from the equation that I just learned, BB is equals to BA plus BA. If I solve this for BBA, it's equals to BB minus BA. All I have to do is X with X's, Y with Y's, and that's it. Okay, so when solving that, so what you will take, you have already a component for I. So I's goes with I's and J goes with J's, and that's it. When I do that, I will get that BBA, it's equals to minus 1050 I minus 692.8 J, and that's kilometers per hour. So what is left for us to do now that I have the vector, I have to change that into scalar values. So in order to get the magnitude of BA, I just have to get square root of its components to the square root of all that, and I get a total of 1258. And please check my math. And if I have an error here, just let me know. And then I need the angle in between them. So that will be inverse tangent of 698, sorry, 692.8 divided by 1050. And that will give me 33.4. That's it. With that, I just solved the exercises using this method. Okay, by utilizing the vectors, I was able to get what I needed. And then after that, the graphical method, I'm going to place this right here so you can see it. I place BA and BB. Remember that you had right here 60, and that's why you have 120. So by using the law of cosines, I was able to find the value, and then by using the law of sines, I was able to find the angle. So guys, with that, we conclude chapter number 12. All right, the last two topics that we covered are very straightforward. I'm not anticipating anything crazy with that. And acceleration and the normal and tangential components are also easy. It's just like getting the equations and getting the mathematical approach is what was a little difficult. But I always like to develop these equations so you can see where they came from, and that way you can utilize them better for your own advantage. All right. I will see you in the next video for chapter number 13. Let me know if you have any questions. Shoot me an email. I'm here for you. All right. Thank you very much for watching.